Welcome to module 6.2. In this module 6.2, we will be talking about the VM instruction set. So, just to sum up what we have done so far, or our understanding, there is a high level language called Jack. We are going to write a compiler later. So there is a proc.jack which is in the high level language. The compiler will translate it to proc.vm. So what are the instructions in proc.vm? That is what we are going to talk about it now. And that proc.vm should now essentially get interpreted into proc.asm. That proc.asm will be in the mnemonics of hack, which we saw, and then the assembler, which we have already written, will make it into binary, which is proc.hack, and we will get execute. So the proc.jack becomes proc.vm, proc.vm becomes proc.asm, proc.asm becomes proc.hack, and proc.hack gets executed on the hack. Now we know how proc.asm gets converted to proc.hack. We also know the mnemonics of that ASM. Now we will understand what are the instructions in that proc.vm and how will it get translated. So each instruction, what is the equivalent translation of that into the mnemonics of hack. So that is what we are going to discuss in this module 6.2 and subsequent modules 6.3, etc. Now what are the instructions that will be part of your virtual machine? There are 4 types of instructions, namely arithmetic instructions, memory access instructions, program flow instructions, function calling instructions. So there are 4 types of instructions, and we will see them one by one very quickly as a part of this module. Now what are the arithmetic instructions? There are 9 types of arithmetic instructions that this virtual machine will support, and note that this is a stack based virtual machine. So all the arithmetic instruction will work on the elements that are on the top of the stack. For example, let us take this one which I am marking here. I have 9 and 4 on top of the stack, right? I have 9 and 4 on top of the stack. I say add. So let the stack pointer be pointing to 102 location, 101 and 100 has 9 and 4. When I say add, what will the operation is supposed to do? It needs to basically pop the top 2 elements of the stack, add them and store it back in the stack and adjust the stack pointer. So what will happen if I say add here? 9 and 4 will be popped out, it will be added 13, then the 13 will be stored here on the 100, and your stack pointer now will point to 101. So this is what should happen. Similarly, when I say subtract x minus y, when I say negate is a unary operation. So I'll just if I'll take y and minus y, I do. If x is equal to y, so eq is the instruction. If x and y are equal, then I need to store 1, else I need to store 0. Similarly, if x is greater than y, x is less than y, now AND of x and y, OR of x and y not. Now when you see, very importantly, 1, 3, 4, 7, 8, 9 are commutative operation. That means even if I swap y and x, right, I call x as y and y as x, still the result will be the same, right. So 1, 3, 4, 7, 8, 9 are commutative operation. That means x operation y is equal to y operation x. But note that, for example, in 3 and 9 are unary operators, so there is nothing like the second operator. But look at second, fifth and sixth instruction, namely subtract, greater than and less than. These instructions are not commutative. That means x minus y is not equal to y minus x. If I am comparing x and y, x for greater than, x greater than y is not the same as y greater than x, or x less than y is not the same as y less than x, right. So at least these 3 instructions are not commutative. So the moment I know that there are binary instructions which are not commutative, binary in the sense I have more than one operand, it is binary. If there is only one operand, it is called unary operation. So in this case there are 2 unary operations, namely neg and not, but all the other things are binary. And if I have a binary operation which is not commutative, I should know where is the left operand and where is the right operand. Please note here x and y. X is the left operand, y is the right operand. In the case of non-commutative operation, this matters. I have to get the correct left operand, I need to get the correct y operand. Simple reason, x minus y is not equal to y minus x, right. So, this is one very very important thing that we need to remember when we are talking about this arithmetic instruction. So, basically in the stack, when I am working on a binary arithmetic instruction, the first, so stack pointer always points to an empty location, the first after that, before that is y and then is x. So, always the right operand which is y, so x operation y is on the immediate top of the stack, immediately after the stack pointer, and x is behind it. So, this we need to remember because we need to handle non-commutative operations as a part of our entire development. So, this is about what we call as the the memory access, the arithmetic and logical instructions, right. And one of the thing that we need to next talk about is memory access commands, right. So, there are two memory access commands. There are two memory access commands, one is push and another is pop. Push means push into the stack, pop means pop out of the stack. Push what into the stack? I need to push some element into the stack. That element is given by segment and index. Similarly, pop, yes, I will pop the top of the stack. To where? I need to specify where should I store the result, to some segment index. So, there are two memory access commands. As we saw, we have 9 arithmetic commands, arithmetic logical, and we have 2 memory access commands. So, right. Now, let us understand what is this whole segment index. That something is new. Push and pop we have already seen. What is segment, what is index? Let us look at, I am having a function. Right. Now, this function requires different types of memory. What do you mean by different types of memory? Or a very proper word is, I need different portions of memory. What are the different portions? As a function, suppose I say function f of int a1 comma int b1, then I have int xyj, right. So, I will be asking for int a1 and int b1. Now, what are the things I have? I have arguments, okay. Then I have local variables, right, at least 2 of them that we could understand, right. So, where are these arguments stored? As far as the VM is concerned, these arguments will be stored in a segment called argument, right. Similarly, the local variables will be stored in a segment called local. What is segment called? No, argument, this means argument is one memory segment which can hold 2 variables, namely a1 and b1. So, argument will be, so when the program is executing, when this particular function is executing, immediately the operating system will create one small piece of memory which can hold, which 2 locations, one which can hold a1, another which can hold b1, and that is part of the argument for this function. Similarly, the operating system will also create a memory with 3 locations, 1, 2, 3, where that's called the local segment, where in the 0th location x will be stored, 1th location and the 2nd location. Okay, right. So as far as this concerned arguments, so you have that entire big RAM, right, data RAM. So when the function starts executing, there will be some space allocated for arguments, some plate allocated for local. Right. So when we are defining the symbol table, right, you remember, you can go back to that exercise, you will remember that you had used a variable called SCL, LCL and another variable called arg, etc., symbol name called arg and LCL. So these are basically those segments. The LCL, right, this LCL is a location, right, it is a location. LCL will store the start address of this local segment, right, and similarly the arg will store the starting address of your argument segment, right. So when this function gets allocated, so this is, let us say this is the RAM, inside that RAM you will have something called arg and you will have something called local. This arg will point to some location here, this local can point to some other location here. Then at this location, please note that I would have created for arg, and here I will be storing the value of A1 and B1, and similarly local I will be storing the value of X, Y and Z. Right. So that is what I mean by a segment. A segment is basically a piece of memory created by the operating system for the function to basically store some of its parameters and local variables, right. Right. So there are many types of segments. We will introduce these segments one by one later, but as far as you understand now, when a function is executing, there are two segments that are necessary. One is for storing arguments, another is for storing local, and this is how they are basically organized, right. Now when I say push segment 0, suppose I say instead of push argument 0, means what? Go to the argument section, go to the 0th index, right, go to the argument section, that means you have reached this storage A1, right. Now take the 0th index there, that will be A1, and push argument 0 means you are pushing the value of A1 into the stack, right. Suppose I say push argument 1, that means go to this argument segment, that is here, go to the first index 1, that is B1, push argument 1 means push the value of B1 onto the stack, right. So this is how, so that is what we mean by segment and index within that segment. Similarly, now I can go and say pop argument, or say, let us say pop local 2, right. So this will go to local, this, and it will go with plus 2 will go to Z. So whatever is there on the top of the stack will be, suppose the top of the stack, somewhere the stack will be inside the RAM, so somewhere let the top of the stack be storing 5000. When I say pop local 2, that means that value 5000 will get assigned to Z here, because local is pointing from there, you take the second location, so that is the location of Z that we have allocated. Now if I say pop local 2 and the top of the stack has 5000, Z basically gets 5000, right. So there are 9 arithmetic commands, arithmetic and logical commands, and 2 memory access commands, namely push segment index and pop segment index, right. So these two are the two memory access commands, and there are at least 8 types of segments. We will talk about that a little later, but you do understand what is a segment here. I have just described it using a very simple function, wherein I said when the function is executing, we need at least 2 segments, one for storing the arguments and another for storing the local variables. Then the next type of instruction that we are going to introduce here are basically program flow commands, and they are very straightforward. The program flow commands are, I have label, symbol, label is a keyword, label symbol, this will declare a label, right. Then there is something called go to symbol. This is nothing but an unconditional jump to the label given by the symbol, and then if dash go to symbol. So this is what we call as a conditional branching. For example, if the previous operation has yielded 0, then it will go to, for example, I can go and say if the previous operation is a 0, just jump to this number. So these are program flow commands in the sense that they alter the, or they dictate the way in which the program basically gets executed. Okay. And the last, so we have, again repeat, 9 arithmetic logical, 2 memory access, 3 program flow, and the last one that we will be discussing is basically function calling programs or function calling commands. And we will have 3 of them, 3 function call. So total number of instructions in your virtual machine is 11 plus 6, 17 instructions in your virtual machine. That's all. And so if I know how to convert each of these 17 instructions into the hack mnemonic, right, then we have understood the translation from the virtual machine to a mnemonic part. So that is the very interesting easy thing. So now what are the function calling instructions? There are 3 types, three function calling instructions. The first one is function name, and n locals. This basically tells you how many local variables are there. Then I have call, the first command. This will tell you how many local variables are there in the function. For example, in our previous case that we described here, this had 3 local variables, x, y and z. Then there is a call, and I have to specify the function name. And it has n args. How many arguments are there? This is another. And then of course the third one is return from the call function. So there are 3 function calling commands, right? So totally 17 commands, and if I know how to translate each one of these 17 commands into its equivalent mnemonics, then the whole thing is then the entire translation process from VM to the thing is done. So now what we need to understand is how we will translate from translate each of these things to VM, and first and foremost we will give an example of how to use these instructions. We will give one case study of how to use these instructions, and then we can go ahead and translate them into the mnemonic of hack, right. So in the next module we will take one example and see through how it basically works, right. So I want you to remember these 17 instructions. There are 9 ALU instructions, 2 memory access instructions, 3 program control instructions or program flow instructions, and 3 function calling instructions. So we will just have an understanding of this, and in the next module we will immediately see an example program how it's getting translated.